Welcome to Lecture 4.1, Numeric Integration for Introduction to Programming in Mechanical Engineering. By the end of this lecture video, you will have an understanding of what numeric integration is, why numeric integration is important on computers, how to apply numeric integration to centroid calculations, and how numerical results can converge to the true values. This slide, the table of contents, contains hyperlinks to each of the sections to make the downloaded PDF easy to navigate. Calculus class probably introduces integration with an image like this, which shows some arbitrary curve with a whole bunch of rectangles underneath it. You are told that the area underneath the curve is approximately equal to the sum of the areas of all of those rectangles, and that is used to lead into the definition for an integral. As the number of rectangles increases, or the number n, the width of each box, delta x, goes down to 0, and the value of the sum approaches the full integral. In math terms, we say that the limit where delta x goes to 0 for the sum of the areas of each rectangle is equal to the full integral. This is the foundation of numeric integration on computers. Rather than doing calculus, we can do algebra and just add it all up. Now, mechanical engineering as a field has a ton of integrals all over. For calculating centroids, which are used in the center of gravity and center of rotation and more, or the first moment of inertia, which is used for rotational speed and energy calculations, or the second moment of area, which is used for bending calculations, or for distributed loads and evaluating the total load and the internal stress profiles. Rather than doing these things by hand, it can be helpful to implement numerical integration. We'll demonstrate this by calculating a centroid. Now recall how to calculate the centroid of an area. The x location is equal to the integral from y1 to y2 of the x location of the centroid of the differential area times the differential area, all divided by the integral from y1 to y2 of the differential area, which is just the total area of the shape. The y centroid is equal to a very similar integral calculation, just using the weighted integral of the y centroids instead of the x centroids. And to be explicit about this, the variables xcdA and ycdA here represent the x and y locations of the centroids of the dA elements within the area. They should be functions of y and of x respectively. Now, because these two integrals are basically the same thing, we'll consider just the integral for the x centroid in this lecture video. And let's start with the denominator because it is simpler after all. So we take the integral over the domain of dA, and we recognize that the differential area is a horizontal rectangle of width x and of height dy. Then the integral is approximately equal to the sum from 1 to n of the finite rectangles which have width x and height delta y. Consider the following triangle. It has side length 3 by 4. The function x of y can be interpreted to be 3 minus 3/4 y. Then evaluating the area with the analytic integral, we just plug in this function for x of y and the limits of integration, which are 0 and 4, and we find that the area is equal to 6. We can also confirm this in our heads with the formula for the area of a triangle, which is 1/2 base times height. Now let's write some code to evaluate this numerically. First, we define an anonymous function to represent x of y. Recall the syntax from lecture 2.1 for anonymous functions. Then let's define the limits of integration y1 and y2 and the step size delta y. We use colon notation here to define an array for the y values at which each rectangle will be evaluated. The syntax for colon notation is listed here. The first element is the start of the array. The second element is the step size between elements in the array, and the third element is the end value in the array. Then we evaluate the quote-unquote heights of each rectangle using the anonymous function defined previously, where the input is the y locations array. We then evaluate the areas of each of the rectangles by multiplying the array x values by the rectangle width dy. And finally, we evaluate the total area by adding up the elements in the delta A values array. This code produces the following result. A is equal to 6.15. Recall that the analytic answer to this is 6. We'll come back to this later. Now let's evaluate the numerator of the centroid calculation. Recall that it is defined as the integral from y1 to y2 of xcdA as a function of y times dA. Given that our differential areas will be shaped as rectangles, the centroid location for each of those differential elements will be the value of x of y divided by 2, and the differential area dA remains the same as x of y times dy. Then the integral is approximated by the sum of, again, the centroid of each rectangle is just x of y divided by 2 multiplied by the area of the rectangle itself, which is again x of y times delta y. To evaluate the numerator numerically, we can add a single line to the end of the previous code, just dividing the array x values by 2, performing element-wise vectorized multiplication with the delta a values array, and then wrapping that in the sum command to add it all up. The result of this is 6.2269. Then evaluating the centroid is as simple as dividing the numerator by a, which results in xc is equal to 1.0125. But note that this value is taken from the base of the triangle, which for evaluating along the y direction lies along the right side at x equals 3. So we should actually subtract this value from 3. This gives us the value 1.9875, where the analytic answer is again 2. But wait, we know that the area should be 6 and the x-centroid should be 2. Why does the code say that the area is 6.15 and the x-centroid is 1.9875? That's because numerical integration is, by definition, an approximation. Recall that an integral is equal to the limit where delta y approaches 0 for the sum over the rectangles of base width and delta y height. Let's return to the example. Let's set dy to 0.01. Recall that it was 0.1 before. Now the area is 6.015 and the x-centroid is 1.9988, much closer to the true answers. To extrapolate this finding, let's look at how the values for area and the x-centroid change with dy. By varying the number of divisions in the domain, the values of each approximation converge towards their analytic values as seen here in these plots. Now the code that was used to produce this graph on the previous slide won't actually be reviewed in this video, but if you are interested, it is provided here on the next slide in the downloaded version. There are a number of things that we haven't covered yet, but feel free to look up the things that you don't recognize. Now for the sake of printing the whole script, the code is split into a couple parts. This is part 1, this is part 2, and this is part 3. Now to summarize, numeric integration is an approach to evaluating integrals whereby calculus is simplified down into algebraic summations. Unlike humans, computers can't just do an integral, but computers are really good at algebra, so numerics play an important role in engineering computation. By first discretizing the domain and then evaluating the function and adding the areas of all the boxes, the numeric approach approximates a true integral, and its accuracy improves as the domain discretization is done with more divisions. By changing that number of divisions, we can approximate the integral more closely.